Okay. Here is in our last class I have discussed about the continuity of a function. Uh, in that in our last session I have discussed about this. That is, we have discussed that uh, there are three conditions. Okay. And these are first one, we have to take f of a whether it is exist or not. If we want to check a function f of x is continuous at x equals to a, to check it we have to, at first we have to find the f of a. That means we have to substitute x by a. Okay. Okay. That I have called functional value f v. Okay. That means, and then number two, we have to check the condition whether a limit approaches to a of f of x, whether this exists or not at x equals to a. To check this, we have discussed that left hand limit and right hand limit both both are equal. If both are equal, then we can say limit x approaches to a f of x exists at x equals to a. Okay. Okay. That is left hand limit, and another one that is right hand limit. If all three are equal, then we can say the function is continuous at that point. Okay. And I have solved one problem regarding whether the function is continuous at any point or not. Okay. Today I will today I will solve another one or two problem. Okay. Okay. Let's move on. Okay. Here, determining whether a piecewise function is continuous at a given number. That means here we are given the function f of x is 4x when x is less or equal 3, and f of x equals to 8 plus x when x is greater than 3. We have to check whether this function is continuous at x equals to 3, number A, and for number B we have to we have to check this function whether this is continuous at x equals to 8 by 3 or not. Okay, so let's move on. First one, how can we check it? Can you solve it? Okay, so do you have paper in front of you? Okay, then try to solve it. Okay. We must remind that we have to take three conditions. Okay. Okay. First one, f of 3, 12. Okay, that is 4 times 3, so 12. Okay, now left hand limit, that is limit x tends to 3 negative f of x. So which function will be considered here? First one. Okay, 4x. Okay. Okay, so the value is 4 times 3 equals to 12, and then right hand limit, that is limit x tends to 3 plus which one? It will be 8 plus x, right? Second one. Okay, so we have here 8 plus 3, right? 11. Now Okay, okay. So, what does it mean? We have here left hand limit is not equals to the right hand limit. That means limit doesn't exist for x equals to 3. So limit x tends to 3 f of x does not exist. So we can say f of x is not continuous at x equals to 3. So that is the solution of A. Okay. Now I think you can try number B yourself. Okay. Complete it now. By 8 over 3. So basically x is 8 over 3. So what is the value of this? Is it 2.667, just like this? So considering this, so you have to find it. So at first you have to find f of 8 by 3. It will be first function. Okay, we have to consider first function for functional value. 8 by 3, that is 10 point. You can keep it in fraction. Okay, 2, 2 over 3, 32 over 3, right? 32, 32 over 3. So that is the functional value now. Find left hand limit. Which one we have to use here for left hand limit? Which function? 4x, right? That is limit x tends to 8 by 3 negative f of x, that means 4x, so equals to 4 times 8 by 3, so we have the same value 32 by 3, right? And for right hand limit, which one we have to use here? Is it 8 plus x? 8 plus x will be used when x is greater than 3, but it's less than 3. It is continuous. Here, here is 8. So for a right hand limit, look at here. For right hand limit, here x tends approaches to 8 by 3 plus. Yeah, you are right. We have to use here 8 plus x. Then we have here 32 by 3, and left hand limit we have 32 by 3, and the functional value, which is 32 by 3. It is all of them are equal, so it is continuous at x, right? Okay, completed. Now second one, I think now you can solve it. Okay, do we need to continue this one? Okay, I will share the slide with you in the Google Classroom, okay, so that you can easily find out what's going on here. Okay, okay, then we can skip it. Okay, okay. Uh, you will try this one at home. Okay, this will be your home task. And here is another one. Here is trigonometric function is used. Similarly, this one is also uh, continuous. Okay, here I have to discuss about this limit. I didn't discuss about this one. Okay, that is the formula basically. If we have limit x tends to 0, sine x by x, the value of this limit is 1. We can directly use it. This is the formula. Basically, there is a proof how we will get the value of this limit 1. No, no, it will be only when x approaches to 0. Uh, and we can also rewrite this as limit x approaches to 0, x by sine x. That is also equals to 1. Similarly, there is another one, that is a limit x approaches to 0, tan x by x, that is also equals to 1. And another one, that is limit x approaches to 0, x by tan x, that is also approaches to 1. Uh, Basically, in limit portion, uh, we have the proof of this. Okay, can show you. Basically, this rule was established or established using Sandwich theorem, basically. Okay, that is this is the theorem. That is a limit theta approaches to zero, sine theta by theta equals to one, and theta is radian. Here is the this is the theorem. This is the theorem. Okay, and they proved it using Sanders theorem. Basically, uh, here is the well, so if we put here limit theta approaches to zero, and here theta limit theta approaches to zero. So the value of these two is 1. So we can say sine theta by theta that is equals to 1. Okay, trigonometry, right? Okay, if you want, then I can discuss about the proof also later. Okay, 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 okay. Now move on to okay. So we can use this directly in the limit. Okay, so that means at x equals to 0. So Here we have 1, and for 0 we have also 1. So we can say here f of 0 equals to 1 equals to limit x approaches to 0 f of x. So all are equal. So we can say here x is continu f of x is continuous at x equals to 0. Okay. Now this one you can try. Okay. This will be your home task. Okay. Now we have some approaches here. That is first one. The value of 1 over x decrease without bound as x approaches 0 from the left. So what will be the value here? That means x approaches 0 from left, since we have here negative sign. So 1 by x equals to negative infinity. Is there any doubt? Here, why negative sign? No, no, look, left. X approaches from left. Since if we draw a number line, if we draw a number line, and here is 0, so from left there is negative infinity, right? So since 1 over infinity, that is 0, but we are approaching from left, so oh sorry, here 1 over 0, okay, that is infinity, undefined, right? Okay, so since we are approaching from left, so that will move to negative infinity. Okay, again, 1 over 0, that is also infinity. But when we are approaching from right, the value moves to positive infinity, right? So we have here positive infinity. And x approaches to 0 plus, that means from right. For this one, x approaches 0 from right. So we have here this positive infinity. Okay. So from here, we can take a decision. That is, since x approaches to 0, if the function is f of x equals to 1 by x, so f of x at f of x, that is the limit when x approaches to 0, then limit of f of x doesn't exist, right? Since we have here negative infinity and this we have here what? Positive infinity. Both are not equal. Okay, here DNA doesn't exist. We will use this concept later. Here is the graph. Here is the graph. F of x equals to 1 by x. F of x equals to 1 by x. So that is the graphical representation. Here, when x approaches to 0. That means at x equals to 0. So we have this line, right? So along with this line, there is no f of x here. That means at x equals to 0, f of x doesn't exist. Okay. Now we have some theorem here also. This is a theorem. Uh, Here, when f of x is equals to 1 over x minus a power n. Here, the graph changes depending on the values of n. If n is an odd positive integer, odd. If n is odd positive integer, then we have the graph which is on the left, this one. But if n is an positive even number, then we have the graph on the right. In both cases, when x approaches to a, limit doesn't exist. Okay, here we have to use this hypothesis. When limit x approaches to a, 1 over x minus a power n equals to positive infinity. When positive even number, positive even, okay, positive even integer. If n is positive even integer, then we will have plus infinity. If n is a positive odd integer, then also we have here positive infinity when x approaches to a from right. Okay. If x approaches from left, then we will have negative infinity. So we can take a decision from here. If n is positive even integer, then we will always get positive infinity. If n is positive even, okay, then we will get always positive infinity when x approaches to a. Okay. But when n is positive odd integer, okay, odd, if n is odd, then x, if x approaches to a from right, then we will have positive infinity, and if x approaches to a from left, then we will have negative infinity. When we get this, if the function is defined as f of x equals to 1 over x minus a power n. Okay. Now, vertical asymptotes. Vertical asymptotes. Uh, what is asymptotes? We all, yeah, yeah, okay. Tell me. Okay, good. Just like this. Here, this line looks like it will touch at infinity, the function, but it will not. So this one is vertical asymptotes, and here similarly, it's like here this line. It looks like so it will touch the function at infinity, but it will not. This one is horizontal asymptotes. So we have here two types. And another one, that is, we have three in total, three types of asymptotes. Okay, vertical, horizontal, and other one angular. That is, if we have a function just like this or just like this, then we will have, yeah, okay. Now, right, this one is neither horizontal neither vertical. Okay, okay. Now, so here, if fx be a function and any of the following conditions hold, any of the following conditions, then the line x equals to a is a vertical asymptote of f of x. Okay, so if x approaches to a from left and we get positive infinity or negative infinity, or even if x approaches to a from right and the limit of f of x is positive infinity or negative infinity, we can say here x equals to a is a vertical asymptote. Even for x equals to x approaches to a and then the limit f of x equals to positive infinity or negative infinity. If any one of these three conditions hold for a that x approaches to a, then we can say x equals to a is a vertical asymptote. Okay, so we can easily find the vertical asymptotes using limits. Here are some examples. Finding a vertical asymptotes. Evaluate each of the following. We are given here f of x equals to 1 over, that is f of x equals to 1 over x plus 3 power 4. So at, if we apply the theorem which we have discussed here, okay, okay, so look at this, x approaches to a x minus a power n, okay, that is equals to, that is equals to positive infinity while n is even integer, okay, positive even integer. Okay, so now here f of x equals to 1 over x plus 3 power 4. So 4 is a positive integer, positive even integer, right? Okay, so if uh, a limit approaches to negative 3 from left, so what will be the value here? Since 4 is an positive even, so we'll have always positive infinity, right? Okay, calculate here directly. Yeah, use the theorem. You can use the theorem directly here. Okay, similarly here, since 4 is also positive even number, right? So that is also positive infinity. And number C, positive even number, so it will be also positive infinity. So now we can say here for this one, first one, here x approaches to negative 3, right? X approaches to negative 3, so we can say x equals to negative 3 is the vertical asymptote of this function. Okay, for all the three cases here, we will have x equals to negative 3 is the vertical asymptotes. Okay. Now, horizontal asymptotes. That is, a line y equals to b is a horizontal asymptote of the graph of a function if either x approaches to infinity, f of x equals to b, that means limiting value. So we can say y equals to b is the horizontal asymptotes of the function y equals to f of x. Similarly, if approaches to approaches to negative infinity also, and we get the value limiting value b, then we can say y equals to b is the horizontal asymptotes. So either here, if x approaches to positive infinity, or even x approaches to negative infinity, and for that, if we get a limiting value, then we can say y equals to that limiting value is the horizontal asymptotes. Okay, here is the explanation. That is, the graph of a function can have 0, 1, or 2 horizontal asymptotes, depending on whether the function has limits as x approaches to positive infinity or even as x approaches to negative infinity. And we are given here f of x equals to this. So if we find the limit x approaches to positive infinity, x approaches to infinity, f of x equals to 3, 5 by 3. So we can say y equals to 5 by 3 is the horizontal asymptotes of the given function. Okay, so we have learned here two processes to find the asymptotes. First one is for vertical asymptotes and second one is horizontal asymptotes. For vertical asymptotes, here we have to satisfy any of the following conditions, right? Here. So then from here, if we get positive infinity or negative infinity as the limiting value, then we can say x approaches to that value, uh, that is x equals to uh, approaching value, x equals to x approaching to, okay, if x approaches to a, then we can say here x equals to a is the vertical asymptotes, and uh, for horizontal asymptotes, if we get if we have the limiting value, then y equals to that limiting value is the horizontal asymptotes. Okay, now here an example. We are given a function and we have to find the horizontal asymptotes of the graph. That is a graph of f. F of x equals to, we are given the function f of x equals to x cubed minus 2 by modulus x cubed plus 1. So we calculate the limit as x tends to positive infinity and negative infinity. Okay. So for x greater than 0, x greater than 0. So that means we will move to positive infinity, right? So if x greater than 0, that means x approaches to positive infinity. So we will have here x cube minus 2 by x cube. Here, since x is positive, so modulus of x cube will be positive, right? Okay, so here then we have to find the limit of infinity, and then we have here 1, so we can say y equals to 1 is one of the horizontal asymptotes. And then for x less than 0, here why they have used here x greater than 0 or x less than 0, can you tell me, can you guess? Right, exactly, good. So since we have here modulus x, absolute value of x, so it can be positive, it can be negative. There are two options. Okay. Basically, there are three options. X equals to 3 is 0, another one. So we don't need to check here since we are finding here the horizontal asymptotes. And as we know, horizontal for finding horizontal asymptotes, we have to find the limit when x approaches to infinity, whether it can be positive or it can be negative, right? That's why we don't need to check for x equals to 0. Okay. So similarly, for x approaches to negative infinity here, we have the value -1. Do I need to discuss about the calculation here? Okay. How can we find the limiting value when x approaches to infinity? We we have to divide numerator and denominator both by the maximum power of x here. Here, okay, if I discuss about this one here, limit, we have solved this type of problem earlier in our first class. I have given you some home task. Have you completed that? Okay, okay, okay. Here, x tends to infinity, that is, x approaches to infinity. We have here x cube minus 2 and here x cube plus 1. So, if we divide both the term numerator and denominator by x cube, then we have here 1 minus 2 over x cube, right? And then 1 plus 1 over x cube. Okay, now if we put infinity, or if we substitute infinity here in place of x, then we have here 1 minus 2 by infinity, 1 plus 1 over infinity. So something over infinity is, what is the value here? 0. Something over infinity equals to 0. So this value is also 0. That means we have here 1, negative 0, 1 plus 0, so it will be 1. That is the 1 here. Similarly for next one. So we have here limiting value negative 1. That means another horizontal asymptotes. That is y equals to negative 1. So in total we have two asymptotes here. Okay, if you notice the graph in the right, you can easily see here this one, this two. Yeah, so this one is one horizontal asymptotes and this one is another one. Okay. We have already discussed about this limit laws. There are some laws, difference laws, constant multiple laws, product laws, quotient laws, power laws, root laws. Okay. Now, basically use of these laws here, but I think we don't need to follow line by line here. We can easily, we can directly apply limits here. Just put negative 3 in place of x. Then we will have here 4 times negative 3 plus 2. So negative 12 plus 2, that is negative 10. Okay. But if we go applying the laws here properly, then we have to calculate 4 lines here. We can easily we can directly apply the limits here. Okay, unless we get 0 by 0, infinity by infinity, or something like this, if we put directly infinity here. Okay. Do you have any other tuition to do? Okay, okay, then we can continue. Okay. Here is another one, that is a rational function. Here also we can apply limits directly here. Okay, so you don't need to apply the uh, quotient law we have here. What was the quotient law? That was limit. We have to apply limit to x square negative 3x plus 1. Again, limit x tends to 3, that is 5x plus 4. That is the quotient law, right? If we have two polynomials here, no, here we don't need to factor it. We can apply directly here. We have to factorize when we get, if we substitute x and we get 0 by 0 form or infinity by infinity form, then we have to do some calculation whether it can be substitute, whether it can be using conjugate, or even uh, you have to expand the terms, and we have to eliminate the term for which we have 0 by 0 form. The proper or perfect example can be here, if x approaches to 1 and we have here x square negative 1 by x negative 1. So we can substitute x directly here. If we substitute x directly here, then we have 0 by 0, right? So in this case, we can't substitute x directly here, and we have to factorize and eliminate the term for which we get 0 by 0 form. And after eliminating the term, then we can directly substitute x. So we'll have here x plus 1, and here limit x tends to 1. So now we can directly substitute x1 plus 1, that is 2. 2 is the limiting value. Okay. And here, problem solving some strategy, which I have discussed now. If we have 0 by 0 after substituting x directly, then we have to do some calculation, whether it can be factorizing, whether it can be using um, conjugate, or even it can be any other calculation by which we can eliminate the term. Okay. I will share with you the slide. Please go through the slide, then it will help you a lot. Okay. Here is the example. We have to factorize and then cancel the term for which we get 0 by 0. So uh, same terms are repeating. Okay, repeating here. That is, we have f of x equals to x squared minus 3x by 2x squared minus 5x minus 3. So if we substitute x equals to 3 here directly, then we have 0 by 0. That means we can't substitute 3 directly, right? Okay. So here, if we substitute x by 3, then we have 0 by 0. So we can substitute x. That means we have to do some calculation here. So here we have to factorize. We have to factorize. And then eliminate the term x minus 3, x minus 3, for which we have 0. Now, if you substitute x, then you will get the limiting value. Okay. Yeah. We when we factor and cancel out the term x minus 3. Since if you substitute x by 3, then 3 minus 3, that is 0. Okay. And after cancelling the term x minus 3, if you substitute, then you will get the limiting value. Now you will not get 0 by 0 if we substitute here after cancelling the term. So that is the limiting. Here is another one. We already used it. Okay. That is, we have to apply conjugate. Right. Right. For this type of problem, we have to use conjugate. We have to multiply both denominator and numerator by conjugate of the radical term. And here, if we are given some complex fraction, then we have to do some calculation at first. After calculating, then we have to apply the limit. These are very simple calculations here. Okay, we also discussed about Sandwich theorem, that is squeeze theorem or pinching theorem. Another name is pinching theorem. And here is a limit. Okay, I need to discuss about this one. Here we are given a limit theta approaches to 0. The function is given 1 minus cos theta by theta. Okay, so to find the limit of this, we have to do some calculation here, trigonometric calculation. So we have here multiplied both terms by 1 plus cos theta. That means we are using here a plus b times a minus b, so we can rewrite it as a square minus b square. That means we can apply the formula here, and also here Pythagorean identity used, that is cos square theta plus sin square theta equals to what? 1. Okay, so from this we can write cos square theta equals to 1 minus sin square theta, and sin square, if we need sin square theta, then we can write 1 minus cos square theta. Yeah, cosine square theta. Okay, so here we have 1 minus cos theta. If we multiply this by 1 plus cos theta, so we have a plus b times a minus b. So we can write 1 square minus cos square theta. So 1 minus cos square theta, that is sin square theta. Okay, and then here we have used product rule. Since we have here several functions, so we can separate this by, here we have sin square theta. That means sin square theta, that means 2 times sin theta, right? Sin theta times sin theta. So we have here theta in the denominator. So if we separate theta just under sin theta, then we can apply a theorem here. Since we know that limit theta tends to 0, sin theta by theta, that is equals to 1. Okay, okay. Now and then here limit theta tends to 0. So if we substitute theta by 0, then we have here sin 0. What is the value of sin 0? No, sin 0 is 0, cos 0 is 1. Cos 0 is 1. Okay, so we have here 0 by 1 plus 1. That is 1 times 0, that means 0. So the value of this limit is 0. Okay, and IVD, that is intermediate value theorem. Uh, we have to use this theorem to find some limiting values. Uh, the use of this theorem is not much. Okay, but the theorem here, what it says, if f be continuous over a closed bounded interval, here is the interval a to b, closed interval. If f is continuous in this interval, and then z, if z is any real number between f of a and f of b, then there is a number c in between the interval a and b, satisfying f of c equals to z. What does it mean? It says that if we are given a function f, okay, and f is continuous in an interval, that is a and b, so in between there will be a value c. Okay, so c, if we substitute f x by c, then that will be z, and z will lies in between f of a and f of b. Here is the graphical representation. If for x equals to a, here is the mm, interval, that is a to b, from here a to b. So in between a and b there is a value c. Okay, and for a, f of a is here, and for b, f of b is here. So in between f of a and f of b there will be a value z. Okay, there will be a value z, and for which we have z we have here for f of c. And that is the theorem basically. And here some key equations based on this chapter. We have discussed all of them: slope of second line, tangent, second line, then average velocity, and then intuitive definition of limit, and two important limits are here. We have to x approaches to a x, then we have to substitute x by a, so the value of the limit will be a, and if there is a constant function, so it will not depend on whether x approaches to what, we'll get the constant term. And then one-sided limit, then infinite limit, then infinite limits to the right, from the from the left, and then two-sided limit, and then uh, important limits here. I have, here is the one, and just now we have proved this, so we can this use this as a, we can use these two limits directly. Okay, and then some key concepts from this limit and continuity. Basically, a preview of calculus. Calculus we have here differential calculus, integral calculus, and then multivariable calculus. And limit is the part of differential calculus. Okay, and then a limit of a function. We already discussed all of them here. And then limit laws. There are some laws based on limit, and then continuity. Okay, that's all from this chapter, limit and continuity.